little review to begin with. We're thinking about inverses. What have we learned about inverses so far? They're reflection over the line y equals x. All the x and the y's change. They change on points on the graph. They change in the equation if you're switching the equations around. And actually right before this, there's a note on the page before that I think it's worth talking about. Right here as a review. And it says, when is the inverse of a function also a function? So for example, we've done parabolas already. And when you switch the x and the y's on that parabola, the inverse looks like this. And can you see that that blue function does not pass the vertical line test? The black one, a parabola, is a function. But the blue one is not a function. So how can we tell, just by looking at the original graph, if the inverse is going to be a function or not? For example, if I do the x cubed graph that we have, its inverse is a function. But if I would do the absolute value graph that we started with, its inverse is not a function.
Is there ever a point when a y value has two x values and it wouldn't be a function?
When a y value has two x values. In other words, what he's saying is this y value is here and it's here. Okay? This one has a y value here and here. Now, how could we summarize that to make it an easier way to check?
It's a function if there's only one y value for a given value of x.
Right. It's a function. So what do we use to check if something's a function? The vertical line test, right? And that vertical line test, if it only hits it once, okay, that makes it a function. So what test could we do on this original graph and on the left here to find out if it's a horizontal line test? So we could write here, when is an inverse of a function also a function? If the original function passes the horizontal line test, then the inverse will also be a function. Wow, that's a funny looking C. Okay? So here, what Spencer was saying is that there's a y value that has more than one x value. We can see that by drawing a horizontal line. And that horizontal line hits 2 points, so the inverse won't be a function. However, on this x cubed graph, as I go along, it always hits only one value. So that means that the inverse of that would be a function. All right, so now we can go back to that example 3 that we had. And we have a parabola. That parabola doesn't pass the horizontal line test, so its inverse won't be a function. But in this question, they say, what happens if you didn't take all of the parabola? You just took a portion of it. Could you take a portion of it so that it passed the horizontal line test? And the first part, the way they say, is could you restrict the domain? Could you only take some x values? Well, a parabola is kind of split in half by the vertex, right? And there's an axis of symmetry. So our vertex on this graph right now is at 1, 3. So if we only considered half of that parabola, for example, if I just took when x is bigger than or equal to 1, I'll draw it down here in blue. Can you see that that would only be this half of the parabola? And if you only considered the blue part, can you see that the blue part passes the horizontal line test? If I just had the blue part, it passes the horizontal line test. If I have the whole parabola, it doesn't. I could do just x is bigger than or equal to 1 as one way to restrict the domain. Or I could take the other half. I'll draw it in green. Can you see that you could have taken this other half of the parabola? How would I write that domain? That's when x is less than or equal to 1. That would be a second way that I could restrict the domain. If I just had the green part, it would pass the horizontal line test. So the question says, determine 2 ways to restrict the domain so its inverse is a function. Well, we've done that. We can take the vertex and do x is bigger than that and x is less than that. Basically cut your parabola in half. Secondly, it says write the equation of the inverse each time and use a graph to illustrate. So what I'm going to do the graph part first. Okay? On my original red graph, I'm going to label some more points. Can you see that you have 2, 4 and 3, 7, and over here you would have 0, 4 and negative 1, 7. And I'm going to color code this on my graph as well. How do we find an inverse? We switch x and y. So if I had 1, 3 on my original one, can you see that you would have 3, 1? If you had 2, 4, here I'm going to 3, 1. If you had 2, 4, you would have 4, 2. And 3, 7 would give you 7, 3. I'm drawing that in blue because that's the inverse of the blue section of my graph. If I did the same with the points on the green part of my graph, switch colors to green, I would still have 3, 1. Instead of 0, 4, I would have 4, 0. And instead of negative 1, 7, I would have 7, negative 1. And this would be that part. So if you had the blue on its own, it would be a function. If you had the green on its own, it would be a function. But if you had both of them together for the inverse, it wouldn't be a function because it wouldn't pass the vertical line test. So I have used colors to demonstrate how one part was an inverse of the other part. So I've used my graph to demonstrate. We want the equation of each of these inverses. So we're going to look, how could you find those equations from the graph? And how could you find those equations algebraically? So you have to decide which one's going to be easier for you. If I want to find the equation of the inverse, split it here. If I want to find the equation of the blue one first, just from my graph, can you see that the blue one is a square root graph? It's got the shape of the square root graph, and it's been moved 3 to the right and 1 up. So if I wrote that out, y equals square root 3 to the right would show up as x minus 3 inside the function. 1 up would show up as a plus 1 outside of the function. For the green one, using my graph, can you see that it's a square root graph? First of all, it's been flipped over the x-axis. Then it's been moved 3 to the right, 1 up. Flipping over the x-axis is a vertical reflection. That would show up as a negative outside of the function. Then we go 3 to the right and 1 up. So I can find those equations using transformations. I can also find those equations algebraically. Algebraically, how do we find an inverse? We switch x and y. So if the original equation was y equals, now we would have x equals, bracket, y minus 1 squared plus 3. And we need to solve for y. So I'm going to get the squared part by itself by subtracting 3 on both sides. And then I could square root both sides. Remember, when you square root both sides, you'd have plus or minus. And then to get y by itself, I'd have to add 1 on both sides. So I get plus or minus x minus 3 plus 1. Notice that the two equations that we got, the blue one and the green one is the positive, one is the negative. How do you know which one goes with which? Okay, we knew which one went with which because we drew the graph first. So the graph is what helped us figure out which one is with which. If we wanted to do it algebraically, okay, how do we figure that out? Well, for the blue one, the domain restriction on the original function was x was bigger than or equal to 1. That means that on the inverse, when you switch x and y, the y has to be bigger than or equal to 1. Look at your equation. Would the positive value make it bigger than 1? Or would the negative value make it bigger than 1? Well, negative would mean you'd start at 1 and subtract stuff. That would make it less. So because on the inverse, the y has to be bigger than or equal to 1, you would know you need the positive one. For the green one, the domain restriction of the original function was x is less than or equal to 1. So that means on your inverse, y would have to be less than or equal to 1. Means that it goes down forever. In order for it to go down forever, you would need a negative in front of that square root. Sometimes the algebra will be easier than the graph. Sometimes the graph is easier than the algebra. We've done both here, but you have to get yourself comfortable with both methods so that you can say, oh, in this case, I think I'd rather use algebra to figure it out. In another case, I think it makes more sense for me to do a graph to figure it out. So let's reread the question, make sure we solved everything. Determine 2 ways to restrict. We've done that first. On a parabola, it'll always be based on the vertex. Yes? Yeah. Secondly, do we write the equation each time? Yes, we did. Once we used the graph to figure it out. Once we did the same thing using algebra. Did we use a graph to illustrate each way? We did. We color-coded so that it was obvious from our graph which part went where. So not only did we show it on our graph, we had to communicate it some way that it was easy to see which one went which. Okay? If this was a test or a quiz, I'd probably even add a note to the person who's marking it by saying the inverse of the blue is shown in blue, the inverse of green is shown in green, just to clarify that that's why I chose the colors that way. Because it might not be obvious to the person who's marking. Okay, questions for practice on this one are 10 and 12.